So, we have discussed the gain of general two port circuits, and we have seen the different gain like power gain, available gain, transducer gain, and we have also discussed the conditions related to the stability of the two port. We have also discussed the conditions related to the stability of the two port device. Let us now move on to discussion of the issues related to the design of a single stage transistor amplifier. So, the maximum power transfer from the input matching network to the transistor and maximum power transfer from the transistor to the output matching network will occur when both input and output they are conjugately matched. That is, gamma in is equal to gamma s conjugate and gamma out is equal to gamma L conjugate. We assume that the matching network that we are designing, these are lossless matching network, and with the assumption of lossless matching sections, these conditions will maximize the overall transducer gain, and we can write GT max, the maximum of the transducer gain, as 1 by 1 minus mod of gamma s square mod of S21 square into 1 minus mod gamma L square divided by 1 minus S22 gamma L mod square. So, in the general case with a bilateral transistor, gamma in is affected by gamma out and vice versa, so that the input and output sections are required to be matched simultaneously. That means, gamma in will be affected by gamma out will be affected by any changes that we make in gamma in. So, we can write from our earlier discussion that gamma in is equal to gamma s conjugate. Therefore, gamma s conjugate can be written as S11 plus S12 S21 gamma L divided by 1 minus S22 gamma L. This is essentially the expression for gamma in, and similarly we can write gamma L conjugate is equal to S22 plus S12 S21 gamma s divided by 1 minus S11 gamma s. So, this right hand side is essentially the expression for gamma out. From these conditions, we can solve for gamma s and gamma L. The solution for gamma s is B1 plus minus root B1 square minus 4 mod C1 square divided by 2 C1, and gamma L is equal to B2 plus minus root B2 square minus 4 mod C2 square divided by 2 C2. Here this B1, B2, C1 and C2, these are given by V 1 is equal to 1 plus mod S 11 square minus mod S 22 square minus mod of delta square. B 2 is 1 plus mod S 22 square minus mod S 11 square minus mod of delta square, and C 1 is equal to S 11 minus delta S 22 conjugate, C 2 is S 22 minus delta S 11 conjugate. So, given the S parameters of the transistor, we can see that we can get the values of gamma S and gamma L. Things become very much simplified if we have a unilateral transistor, that means S12 is equal to 0. In that case, we get gamma S equal to S11 conjugate and gamma L is equal to S22 conjugate, because gamma in becomes is equal to S11 in case of a unilateral device, S12 is equal to 0, and gamma out becomes S22. Now, once we have this gamma S and gamma L computed, now these are the reflection coefficients which are to be seen looking into the matching networks at both ends, and therefore, we can start with Z naught and design a matching network to transform it into an impedance which will give us the required gamma S and gamma L. For a unilateral transistor, GTU max is 1 by 1 minus mod S11 square into mod S21 square into 1 by 1 minus mod S22 square. So, when the transistor is unconditionally stable, K is greater than 1 and the maximum transducer power gain can be simply rewritten as GT max is mod of S21 divided by mod of S12 into K minus root K square minus 1, and we define maximum stable gain that we can get is for K equal to 1, and this is G maximum stable gain, G MSG is mod S21 divided by mod S12. Please note that when S12 is equal to 0, we have a unilateral case, and that is written separately here. So, we can follow the steps for an amplifier design for maximum gain. We check for the stability of the transistor. We have seen that unconditionally stable devices can always be conjugately matched for maximum gain. So, we find out from the given S parameters of the transistors at the specified frequency, we find out gamma S and gamma L, and then we can calculate Gs, G naught and GL, and product of these three will give us the overall gain. And since we know gamma S and gamma L, we can design the matching network using Smith chart by transforming Z naught by the appropriate matching network. Now, matching network can be designed in different ways. We can use section of transmission lines and stubs. We can use L section design that we have discussed. So, design of the matching network is left to the choice of the designer, and also the form in which the fabrication will be simpler. Now, we have discussed how we can design an amplifier for a maximum gain, but in certain applications it may be preferable to design less than the maximum obtainable gain. For example, if we know that higher the gain, the bandwidth will be lower. So, in order to improve the bandwidth, we may sacrifice for gain, or this amplifier may be working as a part of a system where we require the amplifier to provide some specific values of gain. So, we have seen that G naught is essentially mod of S21 square. However, we can achieve gains lower than the maximum achievable gain by designing input and output matching sections to have gains less than their maximum values. That means, instead of designing Gs and GL for their maximum values, we can design them for lower values and achieve the desired gain. The design procedure is facilitated by plotting constant gain circles on the Smith chart to represent loci of gamma S and gamma L that give fixed values of gains Gs and GL. So, we illustrate this procedure with an unilateral case. So, we have Gs given by this expression, GL given by this, Gs is equal to 1 minus mod of gamma S square divided by mod of 1 minus S11 gamma S whole square. Similarly, GL is 1 minus mod of gamma L square divided by mod of 1 minus S22 gamma L square, and therefore, we can have Gs max to be equal to 1 by 1 minus mod S11 square. That means, when we have, since we have unilateral transistor, gamma in is now equal to S11 and gamma in conjugate becomes equal to gamma S, and therefore, this gamma S can be replaced by S11 conjugate. In the same manner, gamma out becomes S22 when S12 is 0, and therefore, GL max becomes 1 by 1 minus mod of S22 square. Now, we define small g s is equal to G s by G s max, and this can be written as 1 minus mod gamma s square divided by 1 minus S11 gamma s modulus square into 1 minus mod of S11 square. And similarly, we define the normalized GL, capital GL divided by GL max is equal to small gl and its corresponding expression. Now, if we fix values of Gs and GL, they represent circles in gamma s or gamma L plane, and their centers and radius are given by Cs Rs for the Gs, constant Gs, and Cl Rl for constant Gl. Now, we can see that the center of each family of circles. So, for different values of Gs and Gl, we can have a family of constant gain circles, and the centers of each family of circles lie along straight line given by angles of S11 conjugate or S22 conjugate. Gamma s and gamma L can be chosen along these circles to provide the desired gains. So, we can plot these circles, family of circles in the Smith chart, and for a given Gs or Gl, we can find out the corresponding gamma s directly from the or gamma L directly from the Smith chart. The choices for gamma s and gamma L are not unique, because we are representing constant gain circles. So, any point on that circle is a candidate, but it makes sense to choose points closer to the center of the Smith chart to minimize mismatch. So, this gamma s and gamma L are chosen on these circles so that it is closest to the center of the Smith chart, and therefore, the mismatch is reduced. We explain here with some numerical values. For example, if an amplifier is to be designed to provide a gain of 12 dB, and at the design frequency, suppose we have S11 is equal to 0.75, angle is minus 120 degree, S21 is 2.83 with angle 80 degree, and S22 is 0.6 with angle 70 degree, and we have already mentioned that S12 is 0. In that case, we find that G naught is roughly 9 dB and Gs max is 3.6 dB and GL max is 1.9 dB. So, what we can do in order to realize this 12 dB gain, we can choose Gs to be 2 dB and GL to be 1 dB. And also we know that this constant GL circle, their center will now lie at 120 degree, because it lies along the line defining the angle of S11 conjugate, Similarly, the other circle will lie at 70 degree. So, these are not exact values, just to show the representative values how we can use this information. For example, this will be GS circle, this may be GL circle, and the points that is closest to the center of the Smith chart and intersecting with this circle is this. Similarly, this is the closest point intersecting with constant GL circle and nearest to the Smith chart. So, we will choose this value of gamma L and this value as gamma S. Once again, it should be noted that these circles have not been drawn to the scale, these are just for representation purposes only. Next, we move on to low noise design. So, we have seen the two cases of single stage transistor amplifier design, designing for maximum gain and designing for specified gain. Let us now consider another issue, the low noise design. So, besides stability and gain, another important design consideration for a microwave amplifier is its noise figure. Particularly in receiver applications, it is often required to have a preamplifier with a noise figure as low as possible. Now, we know that the amplifiers add noise and noise figure is defined as signal to noise ratio at the input divided by signal to noise ratio at the output of the system, and usually it is greater than 1 because of S naught by N naught at the output of the amplifier becomes lower than Si by Ni at the input of the amplifier. So, while designing microwave amplifiers, it is not possible to obtain both minimum noise figure and maximum gain. Some compromise is made where we operate the amplifier at slightly reduced gain to achieve a specified noise figure, and this can be done by using constant gain circles and circles of constant noise figure to select a suitable trade off between noise figure and gain. A noise figure of a 2-port amplifier can be expressed as F equal to F min, minimum noise figure, plus R n by G s into mod of Y s minus Y o p t square. Now, this Y s, G s plus J b s is the source admittance, Y o p t is the optimum source admittance which results in minimum noise figure. So, we can see that when Y s is equal to Y o p t, F become equal to F min, and F min is the minimum noise figure of the transistor, R n is the equivalent noise resistance of the transistor, and G s is the real part of the source admittance. The quantities F min, gamma o p t as we will see, it is related to Y o p t, and R n are the characteristics of the particular transistor being used, and these are called the noise parameters of the device. Now, these parameters can be either provided by the manufacturer in the data sheet or this can be measured. So, we have y s related to gamma s as 1 by z naught 1 minus gamma s divided by 1 plus gamma s. In the same manner, y opt is related to 1 by z naught is related to gamma opt as 1 by z naught 1 minus gamma opt divided by 1 plus gamma opt. Now, in the expression for f, we have mod of y s minus y opt square. So, this term can be calculated from y s and y opt, and also g s, which is the real part of y s, it can be calculated, and then in the expression for f we substitute g s and mod of y s minus y opt square from here, and then we get the expression for f as f min plus 4 r n divided by z naught into gamma s minus gamma opt magnitude square divided by 1 minus magnitude of gamma s square into 1 plus gamma opt magnitude square. Now, for a fixed noise figure f, a circle in the gamma s plane can be obtained from this expression. So, a parameter n, which is the noise figure parameter, is introduced and it is defined as mod gamma s minus gamma opt square divided by 1 minus mod of gamma s square. So, essentially the ratio of these two terms, and then we get this equal to f minus f min divided by 4 r n divided by z naught mod of 1 plus gamma opt square. Now, this expression n is equal to gamma s minus gamma opt magnitude square divided by 1 minus mod gamma s square. It can be written in this form: gamma s minus gamma opt into gamma s conjugate minus gamma opt conjugate is equal to n into 1 minus magnitude of gamma s square, and from this expression we can actually get the equation of a circle, and the center of this circle C f is gamma opt divided by n plus 1, and radius of the circle R f is given by square root of n into n plus 1 minus gamma opt square divided by n plus 1. Now, we see that gamma opt is a complex quantity, and this center C f will lie along a line defined by the angle of gamma opt in the Smith chart. So, let us illustrate the design procedure for unilateral case, that is when S12 equal to 0. We use the data given about the transistor to calculate CF and RF for the required noise figure f. CF lies on the line defined by the angle of gamma opt and center of constant Gs circle lies on the line defined by the angle of S11 conjugate. So, these are the two circles. This is the Gs circle just touching the constant, the circle corresponding to the required noise figure f, and this point of intersection, it is the gamma s, which actually gives the value of Gs for the required f. And once we have this gamma s, we can find out Gs. GL we can find out to be 1 by 1 minus mod of S22 square, because S12 is 0, and G naught is given by mod of S21 square, and we can calculate GTU in dB as sum of Gs, GL and G naught in dB. So, now we have the gain of Gs part designed in such a way it satisfies the requirement of the noise figure f. Once we have gamma s and gamma L, we can see that gamma s value we have already calculated, and once we have this gamma s and gamma L, we can design a matching network following the procedure that is used to transform Z naught to either gamma s or gamma L using stubs, section of transmission lines or lumped elements. So, this is in brief how we can design an amplifier with a specified noise figure, and that design is achieved by adjusting the gain Gs, and we cannot have maximum gain from such design. So, we have discussed different issues related to the design of amplifiers. So, in the next lecture, we will discuss RF oscillators, and we will see some of the steps involved in design of such oscillators.